Hello and welcome. This is the video for AP Physics 1, Unit 3, Circular Motion. Let's get started. This is the MCQ practice, and let's get to our first question. Now, this question is not as much of a math question as it is just of theory, right? What is going on in this question? What is going on in the world without using numbers to quantify it? So, in which of the following situations would an object be accelerated? And then I ask us to select two answers. So let's think about what accelerated means. Accelerated means a change in velocity. And velocity is a vector. It's a speed and it's a direction. So an acceleration would mean a change in the magnitude of that speed or a change in the direction of that speed. Now, a straight line at constant speed, that is not what we are looking for, right? Now, if it moves in uniform circular motion, we know that means that the direction is changing. The speed is not changing. The magnitude of that speed is not changing, but it's moving in a circle. The direction is changing. So that is one of our two answers. Now saying it travels a projectile in a gravitational field, negligible air resistance. Well, if you remember from Unit 1, projectiles do accelerate in the vertical direction due to gravity. That is our second answer, and in this answer, the speed is changing. The direction of acceleration is constant the whole time. Direction of velocity is constant the whole time, but the magnitude of that acceleration, the magnitude of the speed is changing. That's why it's accelerating. And then, of course, it is at rest. Obviously not true. It's not moving at all. Has no velocity. It's not changing. That cannot be our answer. All right, so that was the first question. Pretty simple. Let's get to our next question. All right, a car initially travels north and then turns to the left along a circular curve. This causes the package on the seat of the car to slide toward the right side of the car. Which of the following is true of the net force of the package while it is sliding? This is another one of our theory questions, right? We still haven't gotten into just going through formulas and numbers yet. We're trying to figure out what's going on. Now, when a package is in that car and it's turning, what is happening to that package? Well, there is no force on that package, if you remember, right? Its velocity is still going in the same direction, right? The car is accelerating. The car has its direction changing. The package is staying the same due to inertia. And what our answer would be then is that there is not enough force, centripetal force, to make that package turn alongside the car. That's why the package is still going the same direction it was before. So looking at our answer choices, we need to find something that shows there's not enough centripetal force to keep the package from sliding. Now if we look at it, we see answer choice D. There's not enough force directed towards the center of the circle. The only force directed towards the center of the circle is the centripetal force, so that's our answer. Answer choice D. Alright, on to our next question. We are still not to some numbers yet. I promise we'll get there. But in the meantime, a steel ball supported by a stick rotates in a circle of radius r as shown above. The direction of the net force acting on the ball when it is in the position shown is indicated by which of the following? So recall that the net force, is just mass times acceleration, and since mass is just a scalar, it's just a quantity, the direction of the net force is going to be determined by the direction of acceleration. So what they're really asking us for here is just what direction the acceleration is going in. Now if we look at this, we can see that the ball is traveling in circular motion, right? There is no acceleration other than that circular motion, right? Because only that direction is changing. And in circular motion, the acceleration is always directed towards the center of the circle, which means the force is also directed towards the center of the circle. Looking at our answer choices, we see answer choice D fulfills that. It's force, it's acceleration directed towards the center. Let's move on to our next question. Right, so finally we have some numbers now. Let's see what we can do. A spring has a force constant of 100 newtons per meter, and an unstretched length of 0.07 meters. One end is attached to a post that is free to rotate in the center of a smooth table, as shown in this top view above. The other end is attached to a 1 kilogram disc moving in uniform circular motion on the table, which stretches the spring by 0.03 meters. Friction is negligible, and they're asking us for the centripetal force on the disk. So let's see what we can do here. So they give us 1 kilogram, right? That's the mass. So to find the force, we just need the centripetal acceleration, right? Now let's see what we have here. We see as a force constant of 100 newtons per meter, and its equilibrium position is 0.07 meters. Now it's being stretched at extra 0.03 meters, meaning that the total spring force is 0.03 times 100, or 3 newtons, which is answer choice B. So we actually didn't even need the math, because we have the amount of force that is exerted by that spring. And if we look at it, there is no other force there. The spring force must be the force providing that centripetal acceleration. So answer choice is B. Alright, let's get to some more math problems. An object weighing 4 newtons swings on the end of a string as a simple pendulum. At the bottom of the swing, the tension in the string is 6 newtons. What is the magnitude of the centripetal acceleration of the object at the bottom of the swing? Alright, so let's see what we can do here. We have that the object weighs 4 newtons, and the tension is 6 newtons. And let's draw a free body diagram, right? You might have forgotten those after Unit 2, but let's do this. So we have 4 newtons pointing down. 4 newtons pointing down. And our tension is 6 newtons. And since we're at the bottom of the swing, the tension is directed upwards. So we have 6 newtons pointing upwards, which means that our net force is 2 newtons. And that is our centripetal force. So now we just need to find the centripetal acceleration. Well, if g, right, so 9.8 meters per second, or g acceleration, will give us 4 newtons of force. Right, then 2 newtons of force, since acceleration and the net force are directly proportional, is going to be 0.5 of that gravitational acceleration. And that answer choice is A. And we're done. Let's move on to our next question. Riders in a carnival ride stand with their backs against the wall of a circular room of diameter 8 meters. The room is spinning horizontally about an axis through its center at a rate of 45 revolutions per minute when the floor drops that it no longer provides any support for the riders. What is the minimum coefficient of static friction between the wall and the rider required so that the rider does not slide down the wall? Alright, so this is usually the hardest question you'll get on this unit. And the reason is because you have lots of different units and you have lots of different unknown quantities that you have to work around. So the first thing we see is we see 45 revolutions per minute. Alright, so let's sit back and think about what that means. So we don't have a unit for revolution, right? We don't have that in any of our equations. But 1 revolution is basically just the circumference of that circle, right? It's going around the entire circumference of the circle. And that circumference is 8 pi, because we're given that the diameter is 8 meters. So basically, we've been going, for every revolution, we go 8 pi meters. So 45 times 8 pi meters for every minute. But we don't want it in minutes. We want meters per second because we know how to deal with that. So that would be, instead of a meter, we put 60 seconds. And let's pull out our calculator, which of course you can use on any part of the AP Physics 1 exam. And we get 18.8 meters per second. and that is the velocity, right? So we started off with 45 revolutions per minute. Now we know it's spinning at 18.8 meters per second. All right, so let's erase everything else because we don't really need this anymore. And let's think about how to go next, right? This is one of the reasons these questions are so hard, is because you just have these numbers and you don't really know what to do with them. But they're asking us for the minimum coefficient of static friction. So what does that mean? So if we want a minimum coefficient of static friction, what do we need? We need a normal force, and they're asking us that the rider does not slide down the wall. We also have a gravitational force in play, and our static frictional force is meant to counteract that gravitational force. So let's see. Our velocity is 18.8 meters per second, and we have our diameter 8 meters, so we also have our radius, which is 4 meters. Now we can use some of our circular motion equations. We have that the centripetal acceleration equals the velocity squared over the radius. Using our calculator again, we get 88.8. No, it's flipping towards the edge. 88.8 meters per second squared. Right, so that is 88.8 meters per second squared. That is our centripetal acceleration. And our centripetal force, well, that would just be 88.8 meters per second times the mass. I'm going to put mass in a capital N so that we don't think it's meters. Now, well, now what do we do? Right, so we have a mass, but we don't know what the mass is, right? They don't tell us what the mass is. And we're trying to use this normal force and the gravitational force to find a coefficient of static friction. Well, let's see. The force of gravity is mg, right? So that's 9.8 times m. Well, look at that. Our gravitational force is 9.8 times m, which means that if we want to make sure that the rider does not slide down the wall, we just need to make sure that our static frictional force is at least 9.8 m. And since it's asking us for the minimum, we can just assume it's 9.8 m. So if our frictional force is 9.8 m, and our normal force is 88.8 meters per second squared times m, we can just use another equation that is really not even an equation at all. It's just a quantification of what we already know of friction and the normal force. So we know that mu, right, the coefficient of static friction of S, is just going to be the static friction over the normal force, which is 9.8 m over 88.8 m. And look at that. The mass cancel out. We didn't even need to know what it was. And now, making that equation, 9.8 over 88.8, we get 0.11, and our answer is B. But that was a tough question, but if you can understand how to just change these units, how to effectively use the circular motion formulas, how to always pander to what they're asking for, find the values that they want, then you'll be fine on these types of questions. Right, we're getting to the back half of these multiple choice questions. Right, so we're stuck with another semi-quantitative question, right? It's not, we don't have numbers here, but we do have some proportions that they're asking us to solve. All right, so a ball attached to a string is rolled around in a horizontal circle having a radius r. And if the radius of the circle is changed to 4r, and the same centripetal force is applied by the string, the new speed of the ball is which of the following? Alright, so they're asking us for a speed, right, a velocity. So what do we know about the velocity and about the radius and about the centripetal force? Well, the force, the net force, or the centripetal force, because that's the only force in this scenario, is mass times acceleration, right? Probably heard that a million times by now, but still. But we also know that the acceleration The centripetal acceleration is the velocity squared over radius. All right, so let's think about what this means, right? If we plug in this AC value into the force, then we get m times v squared over r, right? Now this gives us, let's say vi, right? V initial squared over r times m equals the force. Now if we're asking for F equals m v, let's call it F, v final squared over 4r. And basically we want to know what the final velocity is in terms of the initial velocity. Now the same centripetal force is applied both times. Cancel this out, right? If we divided these two, it would cancel out. These two also don't matter, which means that this vi squared over r equals vf squared over 4r. We can take out a factor of r, and we get that vi squared equals vf squared over 4. Right now, we take the square root of both sides. Vi equals, or we can say 2vi equals vf, right, if we carry that forward on the other side. The 2vi equals vf. So the final velocity is twice that of the initial velocity, twice the original speed, and that's answer choice D. All right, let's get on to our next question. All right, a racing car is moving around the circular track of radius 300 meters shown above. At the instant when the car's velocity is directed due east, the acceleration is directed due south, has a magnitude of 3 meters per second squared. When viewed from above, the car is moving, asking us which direction it's moving and the magnitude of its velocity. All right, so let's think about what we have here. All right, so first we want to figure out what direction it's moving. Right now, let's see what we have. When the car's velocity is directed due east, the acceleration is directed due south. Well, let's think about this. When would the acceleration be directed due south? It would be at this point right here, right? Because it's always going towards the center of the circle. So right there, at that moment in time, it would be directed due south, which is also going to be the car's velocity would be directed due east. So it's going around the circle this way, which is, of course, clockwise, right? So we can cross out C, cross out D. Now we just have to find the magnitude, right? So we have a radius, we have an acceleration, we need to find a velocity. Well, we know centripetal acceleration is v squared over r. That would be 3 is v squared over 300. V squared equals 900, and v would be 30 meters per second. Therefore, our answer choice is B, and that is it for the multiple choice section. Let's move on to some free response questions. All right, let's see. A ball of mass m is attached to a string of length L, and it moves in a circle in a vertical plane as shown above. At the top of the circular path, the tension in the string is twice the weight of the ball. At the bottom, the ball just clears the ground. The air resistance is negligible, and they want us to express all answers in terms of m, L, and g. Alright, part A. Determine the magnitude and direction of the net force of the ball when it is at the top. Alright, so what does this mean? So at the top of the circle, they want the magnitude and they want the direction. Well, we're told up here, at this arrow up here, that the ball is moving counterclockwise, right? So if we were like right here at the top, we would be moving counterclockwise. And we can break that acceleration into two parts, because we know that it's going to have one part directed towards the center, like as in all circular motion problems. And the other part is going to be tangential. in roughly the direction counterclockwise. So this is what's going on with that ball when it's at the top. It has force going down, centripetal force, and the force going to the left, which is the tangential force. And the magnitude and the direction of the net force of the ball when it's at the top, well, we need to find that magnitude. So, magnitude of the net force, of course, Fc, as always, is mass times the acceleration. And the acceleration, of course, is velocity squared over r. So velocity squared, that was horrible squared. Velocity squared over r. Alright, so they told us the mass m, right? They just said it's m. They told us the length of the string, it's L. And they didn't tell us anything else. That's it. But they did say that at the top of the circular path, the tension in the string is twice the weight of the ball. Alright, so let's think about what that means. Alright, so twice the weight of the ball. So what does the weight of the ball mean? The weight of the ball is 9.8. 9.8. Try that 8 again. 9.8 m. That's the weight of the ball. Twice that would, of course, be 19.6 m. The 19.6 m, that's what we're working with right now. The tension in the string at the top is twice the weight of the ball. Alright, so what does that mean? So 19.6 m pointed up, and there's 9.8 m pointed down, right? So what does that give us as our net force, right? Let's draw a free body diagram. Think about what this means. So we have this one, right, 9.8 m, and then don't know why I can't draw an 8 today, 9.8 m, and we have a tension, and that is basically it, right? And that tension, well, it looks like the tension's pointed up, right? That'd be the logical thing, right? Because at the top, but the tension is supplying the centripetal force, right? Because nothing else will supply it. So it must be always pointing towards the center of the circle. And if we look at our free body diagram, this one, the one that we drew up here with the ball at the top, we see that it's pointed straight down. Straight down. That'd be another 19.6 m. 0.6 m. Even though it looks like it would be at the top, it actually is pointed down. So for part A, draw part A over here. Part A is 19.6 plus 9.8, 29.4 times m. And what's the direction? Well, in our free body diagram, everything was pointed straight down. So, down. Right, that is part A. Determine the speed v0 of the ball at the top. Right. So B. Now we actually laid most of the framework for how to figure out what V is, right? We wrote up the equation of the Fc equals mv squared over r. Now we just have to quantify that. So we have 29.4 m, right? That's the force, equals m times v squared over r. But r here is L. So we'll just put that L here. Cross out these m's. And then we carry that L. So what we're going to end up with is that v squared equals 29.4 times L. And the answer for v is just the square root of that. So that's our answer for part B. V equals the square root of 29.4 L. Alright, let's move on to part C. Determine the time it takes the ball to reach the ground. The string is then cut when the ball is at the top. So, just looking at this problem, feels like a kinematics problem, honestly. Right, we have a distance that it's above the ground, right? At the top, it would be 2L above the ground. We have a force. Right? The force is 29.4 M. And they're asking us for a time to reach the ground. And, well, what do we know right now? Well, we know that all of the velocity is that tangential point at the top that we see. We know that there is no vertical velocity. So our initial velocity in the vertical direction is 0. Our initial acceleration, our acceleration was constant in the vertical direction, 9.8, or g. We know that, what else do we know? We know the distance, it's 2L above the ground. And they're asking us for a time. Well, we've done this so many times that I think it's kind of obvious what we're going to do next. 2L, right, that's our distance, displacement, equals, we would say v naught of t, but v naught is 0 in the vertical direction, so we can leave it out, equals 1/2 times acceleration, which is g, times time squared. So moving everything over to one side, and everything that we don't want on one side, and then time alone on this side, we get time squared equals 4LG, and time, oh, it's not a t, time equals 2 square root of L times G. And part C is over 2 times square root L dot G. Alright, now last question. At least last part of this question. We still have another free response question to go. Determine the horizontal distance the ball traveled before hitting the ground. This is really feeling like a kinematics problem now. Well, we have a time, and we have a velocity. So, in all honesty, this question is not very difficult at all, because we just say we have our time, right? We have our time, 2LG, amount of time before it hits the ground, and we have a horizontal velocity, which is constant. So this times 29.4 L. So we multiply that, we get 2, of course, we can bring the L out, and we're left with 29.4 G. Which, if you notice, 29.4 is G times 3. So this is like saying 2L times the square root of 3G times G, which is 2LG times the square root of 3. And that is our answer for part D. And this free response question is over. Right, let's get to our last question. Alright, this looks like a tiring question. It's simply because it's so big. To study circular motion, 2 students use the handheld device shown above. Alright, what is this? Let's see what that device is. So it's a glass tube with strength scale. They tell us 5.5 meters, that's the radius, and it's a 2 kilogram mass at the end. Alright, keep going. Which consists of a rod on a spring scale attached. And a polished glass tube attached to the top serves as guide for a light cord attached to the spring scale. A ball of mass 0.2 kilograms is attached to the other end of the cord. One student swings the teal around, I guess that's what they call this entire contraption, around at a constant speed in a horizontal circle with a radius 0.5 meters, and assume friction and air resistance are negligible. Explain how the students, by using a timer and the information given above, can determine the speed of the ball as it is rotating. Alright, we want a speed. Okay, we want the speed of the ball. And what do we have? We have a radius, and we have a mass. So if we had a force right here, we could determine the speed. I don't think we have a force. And they're not telling us a force. So we cannot use that train of thought. But they are telling us that they're going to use a timer. Right, so let's think what we're going to use a timer for. Well, we could determine the angular displacement this goes back through, or at least the linear displacement. So we could time, right? Let's write over here part A. Can you see that? Yeah, you can see that. Way up. All right. You can see that. Part A, using a timer and information given above. So what are we going to do? We are going to time. That was very differently. Going to time the revolutions per minute. Remember the other question when they gave us in revolutions per minute? This is why. It's just easier quantity to calculate. In revolutions per minute of the object, and then you just convert. Let's try that. Convert to meters per second. Like the same thing we did. Right, can you see that? Yeah, you can see that. Alright, that would be part A. Alright, took up too much space because I cannot write small. So I'm going to erase this. Right, if you want to look at it, now's your chance. Alright, let's. It's a pretty simple concept, and I think the reason we could get that is because we had to do that ourselves in that question before, right? Converting it using that quantity. But let's move on. The speed of the ball is determined to be 3.7 meters per second. Assuming that the cord is horizontal as it swings, calculate the expected tension in the cord. So remember when I said before in part A that we had a radius and a mass, and if we had the force, we could find our velocity. And I said we didn't have a force. Well, guess what? Now we have a velocity. So now we can find that force. And that's what they're asking us for, because tension is the centripetal force in this question, right? That tension in the rope is what's giving it the centripetal force. Also, there's just nothing else to provide that force. There has to be the tension. So, of course, we just use F equals the mass times the centripetal acceleration, which of course is the velocity squared over the r. Put out our calculator again. Right, 3.7 squared over r, which is 0.5, times the mass gives us, let's round it off to what, 2 decimal places, 3 decimal places. Right, they gave us 3 decimal places in the question, so we're going to also do that. 5.476 newtons. That is our expected tension. That is our tension force. And the actual tension in the cord measured by the string scale is determined to be 5.8 newtons. What is the percent difference between the measured value of the tension and the value calculated in part B? So before we start, I just want to say this. Percent difference is often a quantity that people calculate wrong. And the reason is that like you find your difference and then you're like, well, which one do I divide it by? And you always divide it by the one that's like theoretical value, right? So if you're doing an experiment, you never use the experimental value. You always use the value that's been accepted. And that accepted value is that 5.476 newtons because that is what it should be theoretically, right? Even though it's like just you, a student, doing it, and you might not have that much authority or something, like that is the accepted value because that is the value that anyone would get if they use these numbers. So we find the difference, right? 5.8 minus 5.476 over the accepted value 5.476 times 100 because we're asking for a percent, and pull out our calculator again. We get 5.917%. Right, on the AP exam, it's always better to just round to 3 decimal places, right? Because that is usually what they want, especially when they give you these values over here in 3 decimal places. They usually just ask for 3 decimal places. That's the best thing to give. All right, last one. The students find that despite their best efforts, they cannot swing the ball so that the cord remains exactly horizontal. And so they're trying and they cannot get it exactly horizontal. Now, what are they asking us? They're asking us on a picture of the ball below. Draw vectors to represent the forces acting on the ball. Identify the force that each vector represents. Well, if we look at our diagram, right, the diagram that they provided us, we can see that the mass is angled a bit down, and I think that makes sense, right? That's just gravity, right? Gravity is going to pull the thing down, right? You can never get around that. So for part for what do we even call this? I, just call it I. Draw vectors to represent this force, right? So we have gravity pointing down. That would be F, G. And we have a tension to the center of the circle. That's F, T. Right, we don't have to put the values in because that's what they asked for. But that is the forces acting on the ball, right? There are no other forces, right? We don't have a normal force. It's not contacting anything. They told us friction and air resistance are negligible, so those forces aren't there. There's just nothing else there, right? This is it. Going all the way over here because kind of run out of space. Part 2. Part I don't know. Explain why it's not possible for the ball to swing because the cord remains naturally horizontal. Well, we just talked about this, right? Because gravity will always pull down. Because gravity will always pull it down, right? No matter how hard you swing it, no matter what you do, if you are on Earth, you are going to have gravitational force. And that gravitational force is going to pull the cord down. And that's why it's not going to be horizontal. But now, right, they're asking us, well, we've accepted that it's not going to swing completely horizontal. But we want to know how much is it not horizontal, right? How much does it, what's the angle that it makes with the horizontal? And looking at the diagram above, right, we see that 500, 0.5 meters, right? We see that distance. That is like our horizontal. And then that rope is the tension. That is our like the not horizontal force that we're trying to calculate how far above the horizontal it is. Now, what we're really trying to do here is, probably need some more space to show this. I'll try. We have a force going like this and like that. This is basically what we have, right? We'll just draw an entire rectangle. And they're asking us for this force. Right, now I drew this thing with the intention of all these lines being parallel. So that's the same as this force. I mean this angle, sorry. And we have that this right here, that is the force of gravity, right? That's the force of gravity pointing down. So that's 9.8 times mass, which is 9.8, 0.2 is 1.96. And then this other one right here, that's the tension force. We got in part B that 5.476 newtons. Right, we're going to use that value instead of the value they gave us, since that is the value it should be. 4, 7, 6. And you notice something, right? You can let's run with this. And if you take that 1.96 that we calculated, I don't know if you how well you can see that, right? But if you take that 1.96 and you take that 5.476 we calculated and use the Pythagorean theorem, you get that the tension of the rope is 5.816. And that's really where they're getting that 5.8 newtons from. That's our hypotenuse, right? That's not one of the legs. That's not what we want. That's why we used the 5.476. Because that is a perfectly horizontal version. This 5.8 right here is the hypotenuse. It's the angled version. That's not what we want. And now, of course, we can just calculate this with a simple inverse trigonometric function. Right, the inverse sine, well, the sine of that angle would be that 1.96 over 5 over the hypotenuse. So let's not use that. Let's use the tangent, right? The tangent of that angle would be 1.96 over 5.476. The inverse tangent of 1.96 over 5.476 would be make sure you're in degrees. You would be 19.7 degrees. Right? 19.7 degrees. I don't express in radians because they're not asking for that right here. 19.7 degrees. And that is the second free response question. That is all the free response questions that we have. And that would be the end of this video. Right, I hope you enjoyed this video. Right, this is the video for all of Unit 3. I made it one video this time simply because there's less content, because this covers less of the AP exam. But tune in next time when we talk about work, energy, and power. See you then.